So hi everyone, today we continue with the second block, and today we're going to get back to the experimentation topic. So as you may remember, like 1.5 weeks ago, we started experimentation, and there was a problem of Bernoulli bandits, like clinical trials. We had several drugs, among which you had a safe drug and a costly drug, and then we had a generalization with like arbitrary number of risky drugs. And then it turned out that the solution to this problem was by the Gittins index. That is, in any point in time, after you have had several experiments with all these drugs, you just collected the numbers of failures and successes for each particular drug. And just using these numbers for each particular drug, you calculated some value which depended solely on these variables, which are specific for this drug. And this is what's called the Gittins index. And then your optimal choice could be characterized as, in each moment in time, you just use the drug with the highest Gittins index. And then you actually acquire some payoff, right? Some results from this usage. It's either 0 or 1. This changes the state variable for this particular drug, and therefore you recalculate the Gittins index exactly for this used drug. And for all other drugs, it stays the same. And then you perform the same procedure by choosing the highest Gittins index and so on. The problem of this solution was that even for Bernoulli bandits, the Gittins index, you couldn't calculate it in closed form. And even an alternative way of solving it with the value function, even with this, you couldn't do, closed form calculations and all that, right? So from the mathematical viewpoint, you kind of solve the problem, but from economical viewpoint, you do not have, enough tractability of the problem. And today we're going to see a model which actually captures all this stuff about experimentation, about all these kind of suboptimal myopic choices in favor of acquiring more information to make better choices in future, in a simpler, framework, where we can obtain in the closed form all the solutions. So historically, they were just two models, which had a great impact on the literature in general. The first one historically was Bolton and Harris, and they built a tractable model for this experimentation. The thing is, for that, they used Brownian motions, right? We studied Brownian motion, so we kind of know it more or less, right? So we could do it, but marginally it's more complicated than the model that I'm going to tell you today. So, and for the Brownian motion, we'll have another kind of topic where we'll use it. So I decided to just tell you one model, which is exactly the second paper, which is Kelly, Ruddy, and Cripps. It provides an even simpler model where all these effects are tractable and you can easily illustrate it. And this model uses Poisson-Frost. So the model itself is the following. So there will be a single agent. Also in the paper, it's more general again than what I will tell you. So it contains results for the single agent and for many agents as well. So, but we will study the baseline case with a single agent. So this agent is exactly the one for experiment. Time will be continuous. So from today, we'll have continuous time models. Continuous time models, and so the horizon is infinite, and the discount rate is just some positive R. Here, the standard terminology here that we call all the options as arms, right? So it's kind of, you remember, it's kind of bandit, right? So in English terminology, a bandit is like, something where you gamble, right? You just pull arms and you wait for the result, and if you have some strikes, you get a reward. So in analogy with that, we call all the options, right, that we have choice between, we call them arms. So the arms are analogs of the drugs in the Bernoulli case model. So we have two options here in each moment in time. They again called safe and risky. The safe is the following. So in each moment in time, it gives you a payoff of S. And it's a flow payoff, right? So if you have some time horizon, let us say of length equal to 1, no matter what unit you use, right? Like 1 second. For instance, then your payoff will be exactly S multiplied by the length of the period, right? So it's kind of a flow payoff. Then you have a risky arm. And this risky arm can be of two types, right? It can be good and bad. If it's good, the following thing occurs. So if it's good, it almost always produces you zero. So it's like, you know, a pulse. So it's like 0, 0, like nothing happens. And then at some random points in time, you actually have arrivals, right? So you kind of have a lump sum which is given to you. And so this lump sum is equal to just a payoff of 1. I mean, like it can be an arbitrary number, we just normalize this payoff to 1. And how these arrivals are distributed, we assume that these arrivals are distributed by a Poisson process, right? Remember that the Poisson process, how we defined it, was a count process. So you have a counter and you start at 0, and then you know, and at time 0, right? And then time goes on, and then at some random points in time you have these arrivals where you add 1 to the count, right? So these are exactly the same arrivals as here. And how we defined like the density of these arrivals was we just specified the distribution function for any interval, right? So we just took an arbitrary interval and we specified like how likely is to have like 0 arrivals, 1 arrival, 2 arrival, and infinitely many arrivals in this particular region. And then we checked that the definition was correct and so on. Alternative way how to understand the Poisson process, which I believe is easier, but I didn't use it in the definition because, you know, then we'll go through it from another angle on it, and it's not very convenient. But what I believe is easier for your understanding sometimes is that how to understand the Poisson process is that it's like you start at 0, at point 0 in terms of time, and then the first arrival occurs in exponentially distributed time, right? So the time in which you have the first arrival is exponentially distributed with parameter exactly the same lambda as we had for the Poisson process. Then after the first arrival, the second arrival is again distributed in the very same way, right? So it's exponential with parameter lambda and so on. It's another property of the Poisson process, so they're kind of related, but I believe it's kind of easier to understand it for you, right? It's kind of when you just specify the density in terms of time of the next arrival time. So that was about the good arm. So almost always it's 0, so it doesn't give you any even flow payoff, right? But at some random points in time, it can give you a lump sum payoff of 1, right? So it's kind of a difference. On the safe arm, you have a flow payoff, right? So the actual payoff depends on how long you use the safe. And this for the risky arm, you almost always have zeros of some kind of inferior things, right? In relation to the safe arm. But then at some random points in time, you have like huge arrivals in terms of, because for the safe arm, when you have marginally small time interval, your payoff is marginally small, right? But here you have kind of a real lump sum payoff. So your payoff is actually 1, not 1 times, let's say, the length of interval. It's actually 1. And this was for the good arm and for the good risky arm. And the bad risky arm, it always gives you a payoff of 0, right? So it's almost the same as a good arm, but without any lump sum arrivals of 1, right? So this is a difference between bad and good risky arms. So you can clearly understand that the bad risky arm is really bad, right? Your aggregate payoff from using it is always 0, right? So the safe arm always dominates bad risky arm. The probability with which this risky arm is good, you have just some prior expectations about that, which are summarized in some initial belief, right? Because you have just 2 possibilities, is it's good or bad, right? Therefore, the whole information is summarized in just the probability with which it's good, right? With the remaining probability, it's bad. So we denote this probability as P0. So it's kind of your initial belief that the risky arm is good. And the question of this model is, okay, you start at 0 with some prior belief, like describe me what you do, right? Your optimal strategy. So here, let us, additionally apply one assumption on the parameters, right? So remember that lambda is exactly this parameter of this pollution process, and S is like the intensity of the safe flow period, right? And what we'll assume is that lambda is higher than S, right? Why it's important? Because assume that you have a good risky arm, right? So you're in this case, right? So you have almost always 0, but sometimes you have arrivals. Then, the only thing that we will need from a Poisson process is just one of its properties, which was specified in the introductory lecture, is that an event, right? So arrival in our case occurs in an interval of length dt, that is, you have a marginally small time interval, right? dt. Then in this length, an arrival occurs with probability lambda times dt, right? 2 arrivals occur with probability something multiplied by dt squared. And remember that it still applies dt squared according to our notations, it's 0, right? So we only use the terms up to the first order of infinitesimally small, right? And therefore, it's kind of a binary things, right? So suppose you are at period at time t, right? And you just, trying to understand what will happen in the next dt period, right? Then there are just 2 possibilities, actually. With probability lambda times dt, you will have 1 arrival, right, of this lump sum. And with the remaining probability 1 minus lambda times dt, you will have no arrivals. Because the probability of 2 arrivals, 3, and so on, it's proportional to the highest order of dt, and according to our notation, it's 0. Therefore, for you, right, when you just consider which arm should I use, the safe arm or the risky arm? For the safe arm, it's quite straightforward, right? If I use it in the time length of dt, right, then my payoff will be exactly S times dt, my aggregate payoff for using it in this interval. For the risky arm, it will be lambda times dt, that is the probability of an arrival, and times the value of this arrival, which is 1, right? That is actually your expected payoff from using the good risky arm, which is certainly good, right? Will be lambda times dt. And therefore, if we assume that S is higher than lambda, right, then actually it's trivial, because you know that if the risky arm is bad, it's certainly inferior to the safe arm. And then if S is higher than lambda, you then know that the safe arm is even superior to the good risky arm, right? And therefore, no matter what type the risky arm is, you would always prefer to use the safe arm. And the problem is actually trivial in this case, right? And we do not want it to be that trivial. And therefore, we assume that lambda is higher than s, which is kind of intuitively clear because lambda is kind of the density of arrivals of these lump sums, right? So the higher is lambda, the more frequent are these arrivals of one. And therefore, the higher is your expected payoff from the good risk arm. So what eventually it gives you is that with lambda higher than s, you certainly prefer safe arm to the bad risky arm, but at the same time, you certainly prefer good risky arm to the safe arm, right? And again, the thing is, you do not know. Initially, you have the some beliefs, but you are not certain, like what type this risky arm is. Is it good or it's bad? So next, one important things to note is that here, once you use the risky arm, right, almost always you have zeros, right, and therefore when you have only zeros and no arrivals from the start of the game, you cannot say, right, whether it's a good arm which just gives you zeros and the first arrivals is quite far from the start, or it's a bad arm which always gives you zero, right? So actually receiving zero in continuous time, you know, it is suggestive about the type of an arm, right? Because you observe that you have no arrivals. So intuitively, you should become more pessimistic about this arm. But at the same time, you know, you are not certain still. But the thing is, once you observe the first arrival of the lump sum, of a lump sum payoff, right, of one, then it becomes perfectly clear, right? Then it becomes perfectly clear for you that you have actually a good risky arm, right? Because lump sums can be produced only by good risky. So here, again, we will use Bellman equation, but in continuous time clearly because the time is continuous for us in this problem. And again, the way how we compose this Bellman equation is basically the same as always. So first we need to specify the state variable, right? Like what determines your decisions in each moment in time. Here in this model is particularly simple because the only source of uncertainty for you in this model, what actually prevents you from making 100% accurate decisions here is that you don't know the type of the risky arm, right? And therefore, your views about this uncertainty are summarized in your current belief with which this risky arm is good, right? So we'll denote this current belief at in moment t as pt. Remember that we have initial value for it, right? It's p0. So it's a starting point in terms of your belief. And we'll use exactly this belief, like believe that the risky arm is good, as a state variable. So we now need to do two things which are standard. First, we'll need to write a Bellman equation, right? To connect your value today from, like in this problem, and kind of your value tomorrow. And remember, in continuous time, your tomorrow is t plus dt time period. And the second thing, we'll need to actually calculate the evolution of the state variable, right? Like how this pt evolves in time, right? So that, because, you know, clearly it somehow evolves because you use some arms and the usage of all the arms as we just indicated before, it's suggestive, right? Because once you have an arrival, you clearly understand that it's a good arm, good risky arm, and therefore your belief instantly jumps to 1, right? So you're kind of certain that this risky arm is good, right? So p is equal to 1. And so alternatively, if you do not receive a lump sum payoff yet, then you become more pessimistic at the same time, right? Because you know, for the bad arm, it's certain that you have no arrivals, but for the good arm, sometimes you have arrivals, and therefore you become marginally more depressed by the fact that you don't have an arrival. So the first thing, like, we need to write an evolution of this state variable, right? How it evolves. First, as I noted, it's straightforward. Like, suppose clearly, I mean, like, if you use the safe arm, right, you get absolutely no information about the risky arm, right? And therefore it doesn't affect the state variable, which is this belief. But if you used the risky arm for some infinitesimally small time period, which is dt in this moment, then there can be two cases, right? Either you had an arrival or you didn't have an arrival. If you had an arrival, as we noted, your belief instantly jumps to 1, right? So in this case, it's quite clear what happens with the state variable. And a tougher thing is to see what happens with your belief once you used for the time interval of dt as the risky arm and you didn't have an arrival. Right. So here is exactly we use the bias rule to calculate this evolution. Remember that for the bias rule, again, we just need a prior. And in the beginning of this dt time interval, your belief was exactly pt, right? So it's your prior with which the risky arm is actually good. And then in the time interval of dt, you didn't have an arrival, right? So how likely is that you didn't have an arrival if the risky arm is good? Remember that you have an arrival probability lambda times dt in the time interval of dt. Therefore, the probability with which you do not have an arrival in this time increment is 1 minus lambda times dt. And you substitute it in two places here. The probability with which you do not have an arrival if the risky arm is bad, which happens with probability 1 minus pt, is actually 1 because you never have an arrival for the bad risky arm. And therefore, your evolution can be written with this bias rule. So here we already see these dt's, right? So let us first simplify expressions a bit. So open all the brackets and collect terms. So here, as you will see, it's like it will be pt minus something small plus 1 minus pt. So in aggregate, it will be 1 minus this, and here it will be this. So at the first glance, it looks like it's tough to do anything else with that. And when you have a fraction as your kind of evolution for the state variable, it's quite tough, right? Because remember, you always need to kind of substitute it next. So, and here is kind of an additional feature of the continuous time. Actually, you can play with the fact that dt squared is actually equal to 0. So what we do, we multiply by adjunct. I don't remember exactly how it's called in English, but with almost the same term where we change the sign here between the terms. So we multiply it by 1 plus lambda times pt times dt. Both we multiply denominator and the denominator. So what we have is like that. So clearly in the denominator, we won't get anything, you know, particularly nice. We'll use it next, but here what we will have will be 1 minus some term which is proportional to dt squared. So actually, in the denominator, the product of these terms is actually equal to 1, right? So I understand it's kind of against math here, but you know, it's how we actually play with these dt's. So that's exactly what you have in the denominator. And now, as promised, you remember that dt squared is actually equal to 0. So here you will have 1 as promised, and here you will have just 3 terms, right? Which you can write this way. Here, let us, you know, do it marginally nicer. So what you see here is that your belief in some small distance from today is almost equal to your previous belief, plus or minus some marginal terms, right? So it's almost as it was like a moment ago, plus some term which is proportional to the length of the period in which you didn't observe in the right. If we want to write it in a slightly nicer form, it will be like that. That is, the change in your belief in time period dt will be equal to minus lambda times pt times 1 minus pt times dt. And that's kind of a very, very standard term for the evolution of beliefs in all the models. So it's kind of, you have a constant which represents the intensity, right? And here is quite intuitive, because if lambda is high, right, that is the frequency of arrivals for the risky arm is high, you have frequent arrivals. Then if you do not observe an arrival, you become more pessimistic, right? And the higher is lambda here, the higher is the depreciation of the belief. And here is the term, which is some kind of quadratic term, pt times 1 minus pt. And it illustrates that your updating belief is the highest when you have the highest uncertainty, right? Because when you have pt being like here, it's around 1/2, but like an intermediate region, then it's kind of crucial for you to have any piece of information, right? So your belief actually reacts to it quite intensely. And for instance, when you have PT being equal to almost 0 or almost 1, right? When you're almost certain about which type this option is, then the change in your belief will be negligible, right? It won't be any change. If you have questions, you can ask sometimes, but I don't know if you have any. So, here, we now specified the evolution of the state variable. So here it's kind of more complicated, right, than in the examples as we did before, because here it's kind of discrete evolution of the state variable, because with some probability, which is lambda times dt, you have an arrival, and then your belief jumps to 1, and then with the remaining probability, which is 1 minus lambda times dt, you don't have an arrival, and then your belief changes like that, right? So it's kind of, we cannot summarize it in a one equation, but it's like that. For instance, if we had Brownian motion bandits, we could summarize like the change in one equation, but it would be more complicated in other dimensions. So here, let us now next understand like how it's optimal for you to behave in this problem. So as in Bernoulli bandits, the logic absolutely stays the same. If you use the safe arm in some time period, you do not get any information about, right? That is, it doesn't update you any belief about the quality of the risky arm. And therefore, the logic, as I said, exactly as in Bernoulli bandits, once you take the safe arm, you stay there forever. Because if at some point in time it was optimal for you to use the safe arm, right, then no information arrives in any time interval, right? And therefore your decision problem actually stays the same. You have absolutely the same belief about the risky arm. And therefore, if it was optimal before, it's still optimal, right? Because you don't have any information any additional information that changes your views. And therefore, we can call this problem as an optimal stopping problem. That is, it can be the case that even from the start, you use the safe option and you use it forever after. But if initially you use the risky option, right? Then the problem is basically when to stop, right? When to be so depressed that you switch to the safe arm and then use it forever after. And therefore, clearly then, because we now know, right, that if you start with some initial belief, and for this initial belief, you prefer the risky arm, then if you do not have any arrivals, right, your belief marginally depreciates, right, like that. So it becomes lower and lower. And like at some point you think that it's not worthwhile to still experiment with this risky option because the belief is too low, and therefore I'll better switch to the safe. That is, therefore there exists some kind of a threshold in terms of your belief level, which we denote as P star, at which you exit experimentation with the risky option, right? Where you become too pessimistic about its prospect. So this is one equilibrium object that we are interested in most, right? Because now, even now, without even solving the Bellman equation, even writing it, we understand it's kind of, you start potentially with the risky option and then at some point you switch, right? The thing, and even like how to calculate the evolution of your state variable. The thing is, you still do not know like the value of this P star, right? Exactly when you should stop, at which point of your loop. And that's exactly what we need to find, right? This threshold at which you decide to stop with the risky option and switch to the C. So how it's done here? Here, in continuous time with binary choice, actually, in each moment in time, we will do the following. It's a general procedure. In the next lecture, we'll do absolutely the same. We will first write the Bellman equation, like for the case when you choose the safe arm. And when you choose the safe arm now, you continue with it forever. Therefore, you can calculate explicitly your value of using the safe arm now, right? And also we will calculate, we will write and therefore then calculate the solution to the Bellman equation, or for the region where your belief is above this P star, that is when you use the risky option, right? And then we will solve these two Bellman equations separately, right? Actually, it will turn out that for the region where you use the risky option, you have a non-unique solution. That is, you have many functions that would satisfy this Bellman equation. At first, it looks quite strange, but then what you do with that, you actually need to glue these parts of the solution to one function, right? And for that, we will need some additional conditions, right? Which will help us to determine exactly this P star. And we will talk extensively about these additional conditions. But the first point is like to understand the Bellman equation for this part, to understand the Bellman equation for this part, and to actually calculate the solutions for this region. So, okay. Here in this case, when PT is smaller than P star, then the value you get is quite simple, right? Because it's the same as just getting flow payoff of S forever after, right? That is, you just calculate it's kind of S. You integrate S from now to plus infinity. You have some discount rate R, and you integrate with respect to time. And it will be equal to just S divided by R, right? In another region where PT exceeds P star, right, when you continue experimentation, here again, like when you're indifferent, do whatever you want. It's not important where you include equality. So here we included equality in this second region. And then in this region, the Bellman equation can be written in this way. So let me clarify why. So your value of using this risky arm today, V of PT, is equal to your current payoff. Current payoff, remember, it's kind of your payoff in infinitesimally small time region dt, right? And here is quite simple to calculate because with probability lambda times dt, right? If the risky arm, like here is it's loss of probability. So let me be like more precise. So if this risky arm is bad, it certainly gives you 0, right? So we do not try. Then if the risky arm is good, which happens with probability PT, right? Then it gives you either zeros or 1, right? As a lump sum. And it gives you 1 exactly with probability lambda times dt. That is, this PT is a probability that the risky arm is good. And this is a probability that if the arm is good, right, then you'll get a payoff of 1. Right? In this time interval of dt. And then you move to the next instant, right? The next instant is t plus dt. So you discount this next instant by a bit, right? And then remember, because you do not know what happens with your belief, right? Because as we noted, there can be two like alternatives. What happens with your belief? It can jump to 1, or it can marginally depreciate. And therefore, I take expectation here with respect to what value function you get in the next instant. And here is exactly the value function at the next instant. Here, expectation is basically with respect to this pt plus dt, right? So these are exactly here it's kind of degenerate Bellman equation, right? It's just a number, actually, which we can easily calculate. Like the value of using the safe option forever after. Here is kind of a meaningful Bellman equation for the risky arm, for the region where you actually use the risk. So next, what we do, we'll just work with this equation, and then we will remember what we got as the value function for the region where PT is smaller than P star, right? And we'll start gluing these solutions together. Let us start. So as promised, with probability PT times lambda times dt, right? Because with probability PT times lambda dt, with the same probability as here, right? You have an arrival in this time period, right? And that's why we have this term where this corresponds to the case when you get the payoff of 1. And exactly with the same probability, you have this arrival, and your belief then jumps to 1, right? If your belief jumps to 1, right, that you are certain that the risky arm is good, then remember that in any instant, right, when you are certain that the risky arm is good, you get exactly lambda times dt, right? Remember, it's kind of with probability lambda times dt, you have an arrival. With probability 1 minus lambda times dt, you do not have an arrival. So your instantaneous payoff is kind of lambda times dt. Your expected instantaneous payoff is lambda times dt. And you just integrate it like from today forever after. There is no uncertainty, right, at this point. And it will be equal to lambda divided by r. That is exactly like the value from the risky arm when you are certain that this risky arm is good, right? Like conditional on the fact that p is equal to 1. And with the remaining probability, right, so which is 1 minus this number, you have no arrival. of the pay, of pay, right, of the lump sum pay. And your belief changes this way, right? And in this case, remember, we need to kind of specify this, right? In this case, we can use the Taylor approximation, which is a standard step, as I hope you remember in continuous time for the Bellman equations. So in this case, the value function with this state variable, we can substitute this term inside here, right? And here, as you see, it's kind of some number minus some small number, right? And therefore, we can approximate it as like the value function exactly at this number, right? And minus the derivative at this point times exactly this marginally small number, right? Again, we just use approximations up to the first order. So clearly, if you use like the normal Taylor rule, you will have like second order of dt and so on. But again, we again use the fact that dt squared is equal to 0. And therefore, we do not have any terms of the second order. So here we just specify like two possibilities, like how your state variable pt evolves. With this probability, it evolves to p equal to 1, and your value function will be like that. And with probability 1 minus this, your state variable evolves like that, and your value function, like this one, will be like that. And therefore, to calculate expectation, here we just need to wait, right? So we need to, here are the weights with which you have either jump to belief equal to 1 or depreciation like that. So with this probability, you will get this value function, and with this probability, you will get exactly this value function, right? So it will be like A multiplied by B plus C multiplied by D. And next, we will just substitute this inside. So let us do this gradually instead. So this is an original Bellman equation that we have. So the first approximation that we make up to the first order, as always, is like, what's the discount rate, right? Here it's like that. This one stays the same. So next, we just substitute what we had before. That is, with probability lambda times pt times dt, this was here, right? We get exactly this value, lambda divided by r, right? So this is the first term here, when we take the expectation, and with the remaining probability, we do not have an arrival, right? And what we get is exactly this value. I wrote exactly this value function because I just do not have enough space, right, to substitute what we obtain. And in the next slide, let us finally substitute what we had obtained here. So eventually it looks like that. So I understand it looks quite tough, right? But you know, here it's kind of, you almost never have any consolations or whatever until the very final moment in these problems, and you have lots of terms. What helps in these problems is that you always need to maintain terms only up to the first order of dt, right? And therefore, for instance, once you have a multiplication of these two brackets, you understand you won't get 4 terms, you will get 3 terms, right? And then among them you will have exactly 1 which doesn't have dt, and 2 which are proportional to dt. Here is again a term which is proportional to dt, and here again you multiply it with something dt. So there will be lots of terms which will actually cancel, right? But initially, when you just substitute all the obtained result, it really looks quite tough. In your problems in the midterm, if we have something like this, and we'll clearly have something like this because we don't have anything else, what I do standardly, you can look at the last year exam, for instance. I always like write what you need to obtain. That is, I explicitly write substitute like what you've obtained here and here, and you should obtain like I explicitly write the solutions that you need to obtain, because I understand it's quite easy to make a mistake in calculation which will affect you long term in these problems, right? And I kind of try to isolate all the parts of the solution so you can control that you do it correctly. So you shouldn't be kind of, you know, you shouldn't ideally make a mistake there. It's kind of more or less like verify that this is like, this is what you should get, but not like obtain from the scratch. So, okay, we substituted everything here, right? And next, we just need to collect all the terms. There is no other way. And as promised, we'll start with these brackets. Like we will have 3 terms. Okay, it probably means that I decided not to go too deep here. So eventually you can even try it for yourself in practice. So here it will be like 3 terms instead of 4. And the only term which doesn't have dt is like v of pt, right? And all 2 other terms will have something proportional to dt, and this one also has proportional to dt. And therefore, once you multiply by this, the only thing that you'll need to multiply by minus rdt, for instance, will be exactly this v of pt. You do not need to multiply all the remaining terms by it. You just need to rewrite them by multiplying with 1. And also by 1, you need to multiply this v of pt. So eventually, can it say it's something nice, but eventually what you get is like that. What is always specific for this problem is that at the left-hand side, you clearly have your value function, right? And your value function should cancel out, right? So the only term which doesn't have a dt, and the second which doesn't have dt in the right-hand side always has to be exactly the value function, right? And all the remaining terms have to have dt terms, right? So it's kind of a law here for these problems. And then what you do, you cancel this value function and divide all other terms by dt, right? And what you eventually get is this Bellman equation, which is a differential equation. Remember that in discrete time, you have difference equation where you have different arguments for the value functions like today and tomorrow. Here you have the same argument, but instead you have a differential equation, right? This prime. Again, here is a differential equation. I do not realize that all of you know how to solve a differential equation. And therefore, kind of your goal would be like to just derive a differential equation. I will write you the solutions, right, which you should get for any differential equation. And here it turns out that the general solution to this differential equation is like that. So it's kind of a linear function plus some kind of tough function here. And more or less, and moreover, sorry, here we have a constant. That is, to some of you who are familiar with differential equations, here it's a first order differential equation, right? It's kind of a specific first order differential equation. It's not regular in many sense, but like if it was regular, first order differential equations, they always have 1 degree of freedom in their general solution, right? And that's exactly this degree of freedom. It's quite easy here to guess the particular solution for this problem, which is, sorry, where am I? So it's particularly easy here to guess a particular solution to this problem, which is just some linear function, right? You can just substitute it and, you know, it will be correct here. So it's like, it corresponds to the case when c equal to 0. And then once you found a particular solution to any differential equation, you can cancel out this term, which doesn't contain this derivative, the terms of v of v prime, right? And then this is called the general equation, right? And for it, it's comparatively easy to construct this general solution. So all in all, it won't be demanded from you to know the solutions to such differential equations. It's kind of things about luck, right? So always you obtain some differential equation in this problem, and then it's up to luck whether it has a solution, like in closed form solution, or it doesn't, right? If it does, it's great. Then you kind of solve the problem. If it doesn't, then depends, right? So sometimes you still can proceed with your model. Sometimes it means that you need to do something else. You won't be able to get until the end there. So in this particular case, it turned out that the authors were lucky, so it has a closed form solution. The thing is, it has a degree of freedom with this constant. So you can substitute any constant here, like 0, 1, or p, or whatever, and this value function will still satisfy the Bellman equation. Also, what we can discuss here is that this solution contains two terms, right? So it's this linear term and this kind of term. And this linear term is exactly the value that you get by forever using the risky arm, right? Because remember, your instantaneous payoff from using the risky arm is lambda times dt if it's certainly good, and it's good with probability pt, right? So it's more or less like pt times lambda times dt. And then you integrate it forever after, so you divide it by r. So it's kind of your belief in the payoff of this risky arm if once you take it now, you use it forever after, right? And this exact term is the value for switching to the safe arm if the risky arm will turn out to be not that good, right? Because here you have more options actually, right? If you have just an option of taking the risky arm and then sitting on it forever after, that's exactly your value. That's exactly will be your value from the start. But here, in any point in time, you have an option of switching to the safe arm if the risky arm will turn out to be bad, but staying on it if it turns out to be good, right? And therefore, like what is clear here is that your value should be higher, right? And that's exactly this additional component which actually makes it higher. So the tough part is actually done. So the tough part is always to do this. So the final part is kind of simple and easy. So now let us count what we do not know. We do not know this constant c, and we do not know this threshold at which you stop experimentation with the risky arm, right? So two unknown. And therefore, we need to kind of find two equations, right? At least two equations, because not necessarily they are linear or whatever, right? But approximately it's always like that. You have two unknowns, likely you need two equations to pin them down. And that's exactly what we do. And we do that exactly by gluing two parts of the value function. Remember that we already found the value function for the cases when p star was below this, when p was below p star, right? And now we found the value function when it's above p star. Right? So now we'll glue these functions exactly at p star. So first condition is always called value matching. That is, it's quite intuitive. The value function should be basically continuous, right? That is, the value like from stopping at exactly P star should be the value from continuing with the risk arm exactly at P star, right? So otherwise, because two parts of this value function, they are both continuous, right? One will be above another for a wrong region, right? And therefore it will violate optimality. So the first condition is quite straightforward. When at P star, you should be basically indifferent between these two options, right? One option is using safe arm forever after, one is like to continue with the risk arm. Both should be fine. Both should give you the equal amount at this P star. That's the value matching. And logically, it looks like we cannot find anything else, right? Because this condition is quite clear. It should be there. But what else can we find? I mean, like, and here it's not the question of like, let us find something which we can apply. Because intuitively, it should, you know, this problem has to have a unique solution, right? Unique optimal strategy. And therefore, something kind of, some law, some additional law has to be satisfied. And it turns out that the second condition is what is called smooth spacing. It turns out that the value function should be not just continuous, but it should be continuously differentiable. That is, the derivatives are exactly at P star, right? When these parts of the value function collide, right? They have to be equal to each other. That is, the derivative from the left of P star should be equal to the derivative from the right of the P star. It's more mysterious, actually, why it's satisfied, and even I don't understand it to full extent all the time. But, you know, no one cares, and always everyone uses it. So here in our particular case, remember that the value of using the safe arm is just a constant, right? Therefore, once we differentiate this constant, it's 0, right? So it's flat to the left of P star, and therefore this additional condition can be written this way. So that's almost it, because we know this value function in general terms, right? So what we'll do, we'll just substitute P star instead of P, and we'll just equate this at P star to S divided by R. And we'll equate the derivative of this with respect to PT, right, at P star to 0. So these will be two equations. So let us do this. So these are exactly the equations. The derivative of this term with respect to P is not nice. Here it's linear term, so derivative is nice, but the derivative of this with respect to PT is clearly not that nice. So it creates this additional term here. But actually, eventually it turns out that, you know, it's quite easy to solve anyway, because you have this first equation. So the first equation is the value matching, right, at P star. So from it, how you do it, you just take this monster, right, all this option value, how you can call it, and express it. It will be equal to S divided by R minus lambda times P star divided by R, right? And you substitute it here, right? And then this monster kind of is eliminated, right? So let's do this, and it will be like that. So it still looks quite cumbersome, but what you can see, you know, you have like quadratic terms, right, approximately, because here you have linear, here you have linear, and here you have division. So once you put it in the left-hand side, it will be quadratic as well, right? And here what is important is that the quadratic terms will cancel out, because if you take a look here, quadratic term will have a coefficient minus lambda divided by R. And here the quadratic term will have the same coefficient minus lambda divided by R. Therefore, quadratic terms will cancel out and you will get a linear equation, right? And therefore it will be particularly simple for you to express P star. And this is exactly the P star. I mean, like I clearly I made all these calculations, you know, it's either you can do them or you can do them, whatever, right? But eventually you have just some answer. What is important about this answer, like this fraction, this p star, is smaller than s divided by lambda. So we can express this term as s divided by lambda plus some additional positive term, because remember lambda, which is intensity of arrivals on the good risk arm, is higher than s, so this term is positive, r is also positive. So you have some additional summand here, and therefore the whole fraction is smaller than s divided by lambda. Why it's important to notice this fact? Because exactly when p star is equal to s divided by lambda, you are myopically indifferent between both options, right? Because when you have pt exactly being equal to s divided by lambda, then remember the safe arm in an infinitesimally small time period dt gives you s multiplied by dt. And the risky arm, again, in the same time period, it gives you, if it's bad, it gives you 0. If it's good, which happens with probability pt, it gives you the lump sum of 1 with probability lambda times dt. So in total, it gives you this instantaneously. And then exactly when pt is equal to this fraction, you are myopically indifferent between these two options, right? And it turns out the belief at which you switch to the safe arm is lower than this threshold, right? That is for clearly than, I mean, like if pt is even higher than s divided by lambda, then, you know, it's clear that the risky arm dominates the safe arm even today and therefore tomorrow. But it turns out that the risky arm also dominates the safe arm within this region, when myopically the safe arm dominates, right? That is, for the beliefs within this region, when you use the risky arm, you behave myopically suboptimal, because myopically it would be optimal for you to use the safe arm. But no, you use the risky arm for these beliefs, right? Because you kind of hope, right? Because when your belief is exactly at this point, right, then myopically you are indifferent between between both options if you use them forever after, right? So it's kind of payoffs are the same, absolutely. But additionally, for the risky arm, right, you have information there, right, which is revealed about the risky arm, because occasionally you can get an arrival of a lump sum payoff, right? This lump sum payoff by itself is already incorporated in this expected payoff. So we do not, you know, count direct payoffs. We count information here, right? And by actually acquiring this lump sum payoff, you can instantly jump to belief equal to 1, and therefore stay forever after. If you have like a failure, kind of like for some time you do not get arrivals, then you can always switch to the safe one, right, and stay with it. But you have kind of an option value here, like occasionally you can get arrivals, and this will, you know, make your payoff jump instantly high. And therefore, for some region below this myopic cutoff level, you still prefer to use the risky arm, because occasionally you can be just lucky, and then you will jump to belief equal to 1 and proceed with this after. The logic here is kind of absolutely the same as we had we didn't have this model, right? But it's kind of the same logic as in standard Bernoulli Bandits model with just 2 drags, right? Because if you are myopically indifferent between the risky option and the safe option, the risky option also has some information value, because it generates additional information, which it can be potentially valuable at the next step, right? And it also has some value for you. right? And this particular model, it incorporates these things that sometimes you do myopically suboptimal actions to just generate more information to make optimal choices in the future. That's why we actually get this result, that PT, that P star, the value of belief at which is smaller than the myopic cutoff. After all, we are not that interested in this constant C that we had in value function, and even in the value function itself, right? Because our goal was exactly to specify the optimal behavior, right? What you should do. And now you clearly understand. You kind of start with your initial belief, and if it was above P star, you just wait until the time your belief reaches exactly this critical level, right? And then you just exit to the safe arm. And if in this meantime you got an arrival, you stay on the risky arm forever. And if your initial belief was below this P star, you instantly go with the safe arm and stay there forever. So in all the cases, we just describe your optimal behavior. So graphically, it looks like that. So here is exactly this part, like this flat part as divided by R up to P star, right? This part of the value function. This is here, it's this myopic cutoff where you are indifferent between these two options, myopic, just today, right? And here is exactly the pinned down value function, right? So that, because understand, right? When we have this system of equations, it uniquely pins down as P star as C, and therefore it uniquely pins down the value function itself, like generally like a function. And here exactly the whole value function is illustrated with this pin down constant C, right? And it turns out it looks like that, right? And here, if you just take something like that, you see it is a value of just, you know, like if you start with some option and continue with it forever after, and with an additional option to kind of switch to the safe arm if the risky arm turns out to be not that good, it increases your value to this. And here, as we discussed before, here you have value matching, that is these parts, you know, they are matched in the same point in terms of value, and it's smooth here, right? So you have that the derivative from the right is also equal to 0, also one from the left. So that's it for today, actually. So we covered this tractable model of experimentation, and now it's actually a workhorse model of experimentation, because understand, when you want to model some kind of learning in your model, and also add some other features, you need an easy model of learning, right? And this model is considered to be a very easy model of learning, right? It has very standard techniques, and once you practice, you get used to it. And so, because you do not, you know, closed formness here, right? You can easily describe what you do in each moment. Then it's kind of easy to add additional ingredients, add this model as an ingredient to your models, whatever, right? To operate with it. The drawback, I mean, like, and it's kind of personal here, is that it's kind of strange a bit in terms of the stochastic process, which underlines this choice between the risky arm, like the good risky arm and the bad risky, right? Because this model is really applicable to cases where you have something like a breakthrough innovation, let's say, as your risky option, right? Because it's like once you have a clear breakthrough that your technology is working, you instantly understand it's working, right? So it really maps more or less how it is in real life, all this revelation of information. But for instance, if you suppose that you have like 2 pockets of milk in your local supermarkets, and you need to choose the one which is the better one, and for instance, you already tried one, so you get used to it, you understand its value, so you can more or less roughly pretend that it's a safe option for you, right? Then the risky brand of milk, it's kind of strange, right? Because it's like, for instance, I try to drink this milk, and then at some random points in time, I have arrivals of something which clearly indicates that this milk is good, right? It's kind of strange. But because a small is kind of tractable and easy and everything, still no one cares. And everyone uses this model to the experimentation. The one with the Brownian motion, which we do not cover, it's more, natural for all this standards application, but it's tougher, and therefore, now it's not that widely used. So that's it for today. Thank you for coming, and let us believe that we will see each other on Saturday. Okay. So that's it, and thank you.
I'm sorry, I have a question. May I ask?
Yes.
Could you please clarify whether the explanations why the derivatives of both value functions in focal P, yes, why they are equal? Is it like is it explained in the paper?
Yeah, I mean, like it's not their invention, actually. I mean, like it's kind of standard. In the next lecture, for instance, we will cover some topic which is much older than these models and still will use smooth pasting. The arguments here are quite, tough, because, it's continuous time, and continuous time is not really easy to operate because you do not have next instance, right, formally. So you divide it in dt's, and this equality of derivatives is related to kind of, if you do not have this equality of derivatives, then you would be able to kind of construct some mixed strategy exactly at the boundary that in the next instant, so it's something like that. Even formally, it's kind of tough to reproduce it. What is even more surprising, for instance, I cannot say it's very old, but like maybe 5 years ago, 7 years ago, there was another paper about another dynamic problem in kind of general settings. And actually in their paper, it turned out that, they have more than two unknowns, right? Here it was just this cutoff and this constant. And they had 3 in their problem. And can you guess what was the third equation? It turned out, yes, that the second derivatives has to be equal to each other. So it looks like it's kind of, some sacred law of nature that has to be satisfied there, that, your solution basically has to be as smooth as possible. Moral, what I can say is that, it's the thing that I just stated, like your solutions has to be as smooth as possible, is actually a better description of equilibrium conditions than this one, because there also exists very similar model to this one, where you have perfectly conclusive bad news. That is, you have arrivals of payoff of -1, which indicates that the risky arm is bad. And in this problem, it will turn out that you actually do not have smooth pasting to be satisfied. When you'll solve all the problems, it will turn out that you have just 1 degree of freedom, for instance. And therefore, what you can, impose is will be just the value match. So turns out that it always depends on how many unknowns you have, right? That is, you just collect the general forms of the value functions from each side of your boundary point, and then just see how many derivatives you should equate such that you know all the constants in your model. I lack a good explanation for why it should be the case, but it's like that. standardly it's like just one derivative. So most of the cases just these two conditions. But as I said, it can be Wild West, it can be just value match, it can be third derivatives, whatever.
Okay, thank you very much.
So that's it. Thank you for coming and see you on Saturday.